You are falling. Not the falling you know, not the stomach drop of an elevator or the brief weightlessness of a stumble. This is falling with no ground coming. Falling where the bottom is not a surface, but a point in space-time where the laws of physics themselves stop working. Falling where the faster you fall, the faster you are required to fall, and where stopping is not a choice the universe will allow you to make. You are falling into a black hole. And the first thing you need to understand, the thing that makes this different from every other death the cosmos offers, is that what happens to your body depends entirely on which black hole you are falling into. Not because different black holes have different rules, the rules are the same everywhere, but because the scale of the object changes everything. Fall into a small black hole, you die before you cross the boundary. Fall into a large enough one, you cross the boundary alive, intact, with no immediate sensation of anything unusual. And then the universe explains, gradually and completely, why that is so much worse. Let's start with a stellar mass black hole, the kind formed when a massive star collapses. 5 to 20 times the mass of our sun, compressed into a region roughly the size of a city, an object so dense that a teaspoon of its material would weigh more than Mount Everest. You are approaching it from a safe distance. The black hole itself is invisible, it emits no light. What you can see is the accretion disk, if one exists, a swirling, superheated disk of gas and dust spiraling inward, heated by friction and gravitational compression to temperatures of millions of degrees, glowing in X-rays so intense they would kill you from thousands of kilometers away if you were not, for the purposes of this, assumed to be approaching in a shielded vessel. At some distance, you leave the vessel. You are now in free fall toward the black hole. And immediately, you feel nothing unusual. This is the counterintuitive reality of gravitational freefall. Because gravity is pulling equally on every part of you simultaneously, there is no sensation of weight. You are weightless, floating. The black hole ahead of you is invisible, its presence betrayed only by the distortion of the star field around you. Light from distant stars bending around the object in front of you, creating a dark circle surrounded by a ring of distorted, brightened stars. It is, briefly, beautiful. Then the tidal forces begin. Tidal forces are the difference in gravitational pull between one side of an object and the other. The moon creates tidal forces on Earth. It pulls the near side of Earth slightly more than the far side, creating the tidal bulge that produces our ocean's tides. The effect on a human body standing on Earth is completely imperceptible. The difference in the moon's gravitational pull between your head and your feet is so small it cannot be measured without instruments. Near a stellar mass black hole, tidal forces are not imperceptible. As you fall closer, the gravitational pull on the parts of your body closest to the black hole becomes measurably, then dramatically stronger than the parts farthest away. Your feet, falling ahead of your head, are being pulled harder than your head. The difference compounds as the distance decreases. The gradient steepens. You begin to stretch, not metaphorically, physically. Your body elongates along the axis pointing toward the black hole as the tidal differential increases. Simultaneously, from the sides, tidal forces compress you inward. The black hole pulls the parts of you closest to it harder than the parts beside you, creating a squeezing effect perpendicular to the direction of fall. Physicists call this process spaghettification, an unusually casual name for one of the more extreme deaths the universe offers. Your body is pulled into an increasingly thin strand, stretched vertically, compressed horizontally, the cells separating from each other,
the chemical bonds that hold tissue together failing under forces that have no biological equivalent. The architecture of a human body dismantled by geometry. For a stellar mass black hole, spaghettification begins well outside the event horizon. You are dead long before you reach the boundary. The tidal forces at the event horizon of a 10 solar mass black hole are strong enough to stretch a human body apart at a distance of several thousand kilometers, far outside the point of no return. You never make it to the event horizon. The black hole does not need you to. But here is where the physics produces something genuinely strange. Scale the black hole up. A supermassive black hole, the kind that sits at the center of a galaxy, millions or billions of times the mass of our sun, has an event horizon millions or billions of times larger. The Schwarzschild radius, the size of the event horizon, scales linearly with mass. A billion times the mass of our sun has an event horizon a billion times larger than a 1 solar mass black hole. But tidal forces scale differently. The tidal force at the event horizon decreases as the black hole's mass increases. A larger black hole has weaker tidal forces at its event horizon, not stronger, because the event horizon is so much farther from the singularity. For a sufficiently massive black hole, anything above roughly 100 million solar masses, the tidal forces at the event horizon are weak enough that a human body could survive crossing them. You could cross the event horizon of a supermassive black hole alive, intact, with no immediate physical sensation of having crossed the most consequential boundary in the known universe. This is the scenario that keeps physicists up at night. Not because it is more violent than spaghettification, it is less violent at first, but because of what comes after. You have crossed the event horizon.
From outside, if anyone were watching, which they cannot be, not in any way that would reach you now, they would not see you cross. They would see something else entirely. Due to gravitational time dilation, time runs slower in stronger gravitational fields. As you approached the event horizon, an external observer would see your image slow down, redshift toward longer wavelengths, and appear to freeze at the event horizon. Your last moment stretched across infinite time, never quite arriving, fading slowly as the photons carrying your image struggle against the gravity that is bending them away. From your perspective, none of that happened. You fell through. Time felt normal. The crossing was invisible. But here is what changed. Inside the event horizon, space and time swap roles. This is not a metaphor or a simplification. In the mathematical description of a black hole's interior, the coordinate that pointed toward the singularity, the spatial coordinate, the direction you could in principle turn around and move away from, becomes time-like inside the event horizon. The singularity is not in front of you, it is in your future. Trying to avoid the singularity by changing your trajectory is as impossible as trying to avoid tomorrow by changing direction. You cannot turn around and fly away from the singularity any more than you can turn around and fly away from next Tuesday. It is not a location you can navigate around. It is a moment in time you are traveling toward. Every moment that passes inside the event horizon is a moment closer to the singularity, not because you are moving toward it through space, but because time itself is carrying you there. How long do you have? It depends on the size of the black hole. For a stellar mass black hole, if you somehow survived crossing the event horizon, which, as established, you would not, you would have a fraction of a second before reaching the singularity. The interior is tiny. For the supermassive black hole at the center of our galaxy, Sagittarius A star, approximately 4 million solar masses, you would have perhaps 20 seconds of proper time after crossing the event horizon before reaching the singularity. For the largest black holes known, the ultramassive objects at the centers of the most massive galaxies,
up to tens of billions of solar masses, you might have hours, days. The interior of an ultramassive black hole is vast enough that crossing the event horizon and reaching the singularity are genuinely separated in time. Hours falling in the interior of a black hole, with a sky that looks, in some directions, like ordinary stars and galaxies, their light still able to reach you as it falls inward, with gravity increasing as you fall deeper, with the tidal forces that were negligible at the event horizon growing steadily as you descend toward the region where the curvature of space-time becomes infinite, and with the absolute certainty that none of it leads anywhere except the singularity. Here is what nobody can tell you with confidence: what happens at the singularity. The singularity is the point at the center of a black hole where the known equations of physics produce infinities, infinite density, infinite curvature, infinite tidal force. In mathematics, infinities are signals that the theory has reached its limits, that you are asking a question the theory cannot answer because the theory is incomplete. General relativity, the framework that predicts the singularity, is our best description of gravity and space-time at large scales. Quantum mechanics, our best description of physics at the smallest scales, predicts different behavior at extreme densities. These two frameworks are not reconciled. We do not have a complete theory of quantum gravity, a framework that correctly describes physics where both extreme gravity and quantum effects are simultaneously important. The singularity is exactly where we need such a theory, which means the honest answer to what happens to your body at the singularity is this: we do not know. The equations stop working. The physics we understand stops applying. Whatever happens at the singularity is outside the reach of the best physical theories humanity has ever constructed. Some physicists believe the singularity does not physically exist, that a complete theory of quantum gravity would show that something happens before infinite density is reached, some quantum process that prevents the singularity from forming. String theory, loop quantum gravity, and other frameworks all predict modifications to the classical picture. Some predict a bounce, the collapsing matter reaching a maximum density and then expanding outward into a new space-time region, as Poplawski's model suggests. Some predict something else entirely. None of these frameworks is confirmed. None makes predictions precise enough to test with current experiments. The singularity remains a mathematical location that no theory adequately describes and no observation has ever probed. There is one more layer to this that the physics forces us to confront: the information paradox. Quantum mechanics has a foundational principle called unitarity, the principle that information is conserved. The complete quantum state of a system at one moment determines its state in all future moments, and the process is reversible. Information is never truly destroyed. It may be scrambled beyond practical recovery, but it is preserved in principle. Black holes appear to violate this. When matter falls into a black hole, its information, the quantum state of every particle, every atom, every molecule of the infalling matter, appears to be lost. The event horizon prevents it from escaping. The singularity destroys it, and when the black hole eventually evaporates through Hawking radiation, a process that takes longer than the current age of the universe for any black hole of stellar mass or larger, the radiation that emerges appears to carry no information about what fell in. Stephen Hawking argued for decades that information was genuinely lost in black holes, that black holes were the one exception to the conservation of information in quantum mechanics. Most physicists found this deeply uncomfortable. A universe where information can be destroyed is a universe with a different and more disturbing character than one where information is conserved.
In his final years, Hawking changed his position. He, along with Malcolm Perry and Andrew Strominger, proposed that information might be preserved on the event horizon, encoded in what they called soft photons and soft gravitons, subtle modifications to the quantum state of the horizon that carry information about infalling matter.
The debate is not resolved. The information paradox is one of the most actively studied problems in theoretical physics. Its resolution, when it comes, will require reconciling general relativity with quantum mechanics in a way that has not yet been achieved. Which means that falling into a black hole is not just a question about what happens to your body. It is a question about whether what you are, the information that constitutes you, the quantum state of every particle that makes up your existence, survives in any form at all. Let's come back to the beginning. Quietly. You are falling. If the black hole is small, you die before you reach the boundary. Your body is stretched apart by tidal forces in one of the most mechanically extreme deaths available in the known universe, in a region of space where no rescue is possible and no signal for help would reach anyone in time to matter. If the black hole is large enough, you cross the boundary intact, and you fall through an interior where the singularity is not a place, but a time, where your future contains with absolute physical certainty a point beyond which no theory currently describes what occurs, beyond which the concepts of space and matter and information all reach their limits simultaneously. In neither case do you come back. The event horizon is the universe's only perfect one-way door, not locked, not guarded, just geometrically, permanently, completely one-directional in a way that no technology and no physics and no amount of energy can overcome. Everything that crosses it goes one way. Everything. Black holes are the most extreme objects the universe has produced in 14 billion years of existence. They are the endpoint of stellar evolution, what remains when the largest stars run out of fuel and collapse under their own gravity. They are the anchors of galaxies, sitting at the centers of almost every large galaxy we have observed, having grown by consuming matter over billions of years. They are the objects that bend space-time most severely, that slow time most dramatically, that push the known laws of physics closest to their breaking point. And they are common. There are estimated to be 100 million stellar mass black holes in the Milky Way alone, supermassive black holes at the centers of the hundreds of billions of galaxies in the observable universe, intermediate mass black holes whose existence is still being confirmed, possibly primordial black holes formed in the early universe, small enough to fit in your hand, dense enough to pull you apart from across a room. The universe is full of these objects, and every one of them is doing the same thing, warping space-time around itself, bending light, slowing time, waiting with the patience of something that does not experience time the way we do, for whatever matter comes close enough to cross the line. You will never fall into one. The nearest stellar mass black hole is approximately 1,000 light-years away. The nearest supermassive black hole is 26,000 light-years away at the center of our galaxy. The distances are too vast, the trajectories all wrong, the probability of an encounter within any human lifetime effectively zero. But the physics is real. The spaghettification is real. The event horizon is real. The interior where the singularity is your future rather than your location is real. The information paradox is real. The moment where the equations stop working and the universe refuses to tell you what comes next is real. It is all happening right now in the dark between the stars to matter that fell in before the Earth existed, stretched, compressed, carried toward a point that physics cannot describe. And the universe, which has been doing this for billions of years and will continue doing it for billions more, has not once felt the need to explain what happens there.